Hi everybody, Mrs. Pesic here. We are looking at section 3.3, Properties of Logarithms. The learning objectives are to use the change of base formula to rewrite and evaluate logarithmic expressions, to use properties of logarithms to evaluate or rewrite logarithmic expressions, use properties of logarithms to expand or condense logarithmic expressions, and to use logarithmic functions to model and solve real-life problems. Sorry about the typo there. All right, so that's our charge for today. So first of all, what is this change of base formula? Well, back before they had the TI Nspire, only 5 years ago or so, maybe your older siblings had like a TI 83 or a TI 84, and they would have had to have learned this. So it's not like this is like 100 years old that they would have to use it, just like 5 years ago. And, well, frankly, at many schools, they don't use the TI Nspire. They still use the TI 83 or 84. So, in other words, if you wanted to find, for example, log to the base 2 of 7, that means 2 raised to what power gives me 7? It's going to be some kind of decimal, all right? Something probably a little bit less than 3, because 2 to the third would be 8. So it's probably 2 raised to the 2 point something. Anyway, to figure this out, you would have to do this complicated change of base formula. Maybe it's not that complicated, but you would choose a base that was on your calculator, for example, a common log like base 10, and you would rewrite this as log to the base 10 of 7 over log to the base 10 of 2. And divide those two and you'll get your answer. So let's test this with our calculator to see if this gives us the correct answer. So if I pull up our calculator and I go to a Scratchpad page and I do log, let's just say we're going to use base 10 of 7, and I want to divide that by log to the base 10 of 2. And when I do that, my answer turns out to be about 2.8. As I was predicting, it was going to be right around 2 point something. So let's just check it, because with your Nspire, you can handle bases like base 2. So let's do that. Let's compare what our answer would have been if we were able to solve it directly, which we are because we have the Nspires. So log to the base 2 of 7, does that give us the same answer? Yes, 2.80735. So this is change of base formula. Again, very handy, very necessary for anyone who does not have a TI Nspire and wants to evaluate something that does not have one of the 2 standard built-in bases. The 2 standard built-in bases are base 10 or base E. All right, so again, if we wanted to solve this same problem, let's log to the base 2 of 7 using base E, we could have just said log to the base E of 7 over log to the base E of 2, which you know could be written ln of 7 over ln of 2. So you can try that one out yourself on your calculator and see if you still get 2.8 as your answer. All right, so that's the change of base formula. All right, and we're going to skip that part. So the properties of exponents have corresponding properties involving logarithms. So for example, a to the 0 equals 1, so log to the base a of 1 is equal to 0. Let's look at these properties of logarithms. First of all, let a be a positive number such that a is not equal to 1, and let n be a real number. If u and v are positive real numbers, then the following properties are true. Let's take a look at the product property. Product property says that the log to the base a of 2 things being multiplied together is going to be equal to the log to the base a of one of them plus log to the base a of the other. So just very important to note, it's not log to the base a of u times v equals log to the base a of u times log to the base a of v. If it's multiplying over here, if this is multiplication here, multiplication, over here when we pull it apart, we need an addition sign. All right, same thing holds for natural log. So natural log of u times v is going to be natural log of u plus natural log of v. Maybe you're skeptical. Let's take a look at this example and see if it works. So here we're using this first property, which is called the product property. And we want to see, is the log to the base 2 of 4 times 8 really equal to the log to the base 2 of 4 plus log to the base 2 of 8? Let's test it. Well, I know 4 times 8 is 32. So I get log to the base 2 of 32. And I want to know, question mark, is that equal to log to the base 2 of 4 plus log to the base 2 of 8? Well, I know that log to the base 2 of 32 is equal to 5. This whole thing is equal to 5 because 2 raised to what power gives me 32? 2 to the 5th gives me 32. And is that equal to what's on this side? Well, log to the base 2 of 4 is 2, right? Because 2 raised to what power gives me 4? And 2 raised to what power gives me 8 is 3. So is it true that 5 is equal to 2 plus 3? You betcha. So that works. That is the product property at work. Property 2 is the quotient property, which says if you are dividing two numbers before you take the logarithm, you can write it as two separate logarithms pulled apart with a subtraction in between. So log to the base a of u divided by v is going to be log to the base a of u minus log to the base a of v. Let's take a look at an example of this. You're supposed to verify that the following is true. So how do we know that log to the base 3 of 3 over 81 is equal to log to the base 3 minus log to the base 3 of 81? Well, I know that I can reduce this. 3 goes into 3 once and into 81 27 times. So this is really log to the base 3 of 1 over 27. All right? And that is going to equal what? Well, 3 raised to what power gives me 1 over 27. I hope you are good with these, and you know that this is negative 3 here. 3 to the negative third is going to be 1 over 27. So this left side of the equation is just equal to negative 3, and we're wondering, is that equal to log to the base 3 of 3, which is just 1, minus log to the base 3 of 81, which is 4. So I get negative 3 is equal to 1 minus 4. Sure it is. Negative 3 equals negative 3. So this quotient property does work. One more property, and that is the power property. This one says log to the base a of u raised to some power n is equal to n times log to the base a of u. Same thing with natural log. Natural log of u to the n is going to be n times natural log of u. So whatever the power is here, it can be brought down in front of the logarithm. So let's verify this one to make sure this is true. Is log to the base 5 of 5 to the third equal to 3 times log to the base 5 of 5? Well, let's evaluate this. On this left side, this is log to the base 5 of 125. 5 to the third is 125. Is that equal to 3 times log to the base 5 of 5? Well, what is log to the base 5 of 125? 5 raised to what power gives me 125? That's equal to 3, because 5 to the third is 125. And is that equal to 3 times, what is log to the base 5 of 5? Well, 5 raised to what power gives me 5? 1. Sure enough, it does work. 3 equals 3. Our power property does work. All right, so let's take a look at this example. You're writing each logarithm in terms of ln of 2 and ln of 5. So in this case, you have ln of 10. Let's rewrite this in terms of ln of 2 and ln of 5. Well, we're going to do that by saying ln of 2 times 5, right? Because 2 times 5 is 10. And then using the product property, we can split this up and write it as ln of 2 plus ln of 5. And that's all you have to do for that problem. Let's take a look at this next one. Ln of 5 over 32 is going to be equal to ln of 5 minus ln of 32. And that's pretty good, but we're supposed to be writing everything in terms of just ln of 2 and ln of 5. So we were able to do that here. We've got just ln of 2 plus ln of 5, but here we've got ln of 5 minus ln of 32. Well, let's fix that. Can we write 32 as with 5 as the base or with 2 as the base? Well, we can write this as ln of 2 to the 5th. So I have ln of 5 minus ln of 2 to the 5th, and you know from the power property that this exponent here can come down in front. So we can write this as ln of 5 minus 5 times ln of 2. All right, so that's being able to rewrite, you know, some expressions in terms of other expressions using our properties of logarithms. All right, let's take a look at these examples. Find the exact value of each expression without a calculator. So if we have log to the base 5 of 7th root of 5, and we want to evaluate this without a calculator, well, I want to remind you that if you have 7th root of 5, that's the same as 5 raised to a rational power. Do you know what the rational exponent would be? If it's 7th root, that would be same as writing 5 to the 1/7 power. So let's do that first. Log to the base 5 of 5 to the 1/7 power. Using our power property of logarithms, this 1/7 can come down in front. So we can write this as 1/7 times log to the base 5 of 5. And you should be recognizing log to the base 5 of 5. That's really just equal to 1, because 5 to the first is equal to 5. 1/7 gives me the answer of 1/7. No calculator needed. All right, and let's try this next one. We've got ln of e to the 12th plus ln of e to the 5th. Again, these powers can come down in front. So I can write this as 12 times ln of e plus 5 times ln of e. And I'm hoping you recognize right now that ln of e is really equal to 1, because log to the base e of e is 1. So I get 12 times 1 plus 5, again, times 1. So that gives me 12 plus 5 is 17. Look, Ma, no calculator. All right, and let's move on. All right, when you need to solve logarithmic equations, it is often helpful to rewrite them in a different form, either by expanding or condensing. So let's try this out. So if we're going to expand log to the base 4 of 3x squared y, that means we can use our properties, the product property, quotient property, and power property to help us do that. First of all, if you've got a bunch of things being multiplied together, then you can split it all up and write it as separate logarithms. We're expanding, so we're going to write log to the base 4 of 3 plus log to the base 4 of x squared plus log to the base 4 of y, because these were all being multiplied here. It was 3 times x squared times y. We can pull it apart, write them as separate logarithms with addition in between. And one last step here in expanding, don't forget any exponents can be brought down in front of their respective logarithms. So we get log to the base 4 of 3 plus 2 log to the base 4 of x plus log to the base 4 of y. And we're done. We expanded this logarithm as much as we could. All right, let's try this one. If we're going to expand this logarithm, this is a quotient, so we can use the quotient rule. So that says ln of square root of 4x plus 1 minus ln of 8. And remember that if we have a square root radical, that's the same thing as raising our quantity 4x plus 1 to some rational exponent. In this case, it's going to be to the 1/2. Minus ln of 8 is still there. And don't forget, this 1/2 can be brought down the front. So we get 1/2 times ln of the quantity 4x plus 1 minus ln of 8. And this is our answer for expanding this logarithm. All right. Let's look at how to condense some logarithms. We're condensing 1/3 log x plus 5 log of x minus 3. By the way, notice no base is written here, so it's understood to be base 10. All right, but we don't need to write those in. It's understood. This 1/3 right here, if we're going to try and condense, we're going to put that as an exponent on the x. So that's log of x to the 1/3. And again, this 5 can come up as a power on the x minus 3. So I get plus log of x minus 3 raised to the 5th. Notice that I am adding 2 logarithms, so I can rewrite it as just 1 logarithm, but I'm going to have to multiply that. So I get x to the 3rd times the quantity x minus 3 to the 5th. All right, and maybe it would look a little bit better if I used brackets here. So I'll say log of x to the 1/3, which I could actually write as cubed root of x, times x minus 3 to the 5th. And I put the whole thing in a bracket. All right, that is condensing. This was the expanded form, if you will, and this is the condensed version. All right, let's condense this next example. This one says 4 times ln of x minus 4, so let's bring that 4 as an exponent here. Same thing here, bring this 2 up as an exponent, so I get ln of x minus 4 to the 4th minus ln of x squared. Since we are subtracting two logarithms, we can rewrite this with a quotient. So let's write this as ln of x minus 4 to the 4th over x squared. All right, and that's all condensed. That's as much as we can do with that. And let's try this one. If we have 1/5 times log to the base 3 of x plus log to the base 3 of x minus 2, let's work from inside out and try and condense what's inside first. I see an addition here, which means I can rewrite it as one logarithm, but with multiplication. So let's write this as x times x minus 2. And don't forget that this was really a 1/5 out in front of this. So that means I really could rewrite this, bringing that 1/5 as a power. All right, on the whole quantity there. So I'm going to have log to the base 3 of x times x minus 2 to the 1/5. And you know 1/5 means 5th root. So I could write my final answer as log to the base 3 of 5th root of x times x minus 2. All right, that is an example of condensing. All right, and well, I really like this example, but I figured this video is long enough already. So I will just ask you to look at example 7 on page 242. It's a nice real-life example of how logarithms are used, and it's a way of finding an equation that relates the distance that a planet is from the sun with how long it takes for the planet to revolve around the sun. And so it's a nice example of how logarithms can help us get a nice equation for that, for the relationship between those two quantities. Okay, so you're going to look at example 7 on page 242, and that brings up your homework, which is section 3.3, page 243, vocab 1 to 5, and I tried to make this as gentle as I could. I'm just asking you to do 5 to 75 multiples of 5. That's not that many problems. And then you're going to also do 79, 80, 81, and 84. All right, so that's the end of this video, and I hope you took good notes, and I hope that you are very successful at doing the 3.3 homework. When we meet again, we will be looking over this homework and also looking at section 3.4. All right, have a good day, everybody. Thanks for watching.